Okay, so here's a little kind of just a little follow-up with exponential and linear here. So on this one, I always look for linear first. So if you kind of look, this is going up by 6, up by 6, up by 6, up by 6, up by 6. So that tells me it's linear because it's a constant change all the time. And real life starts at 0, right? If you're 1 years old, you've already lived a year. So everything starts at time 0. That's your start. And so if I know this is linear, then I can write my formula because I know my linear formula is going to have my starting amount. And then I'm going to either add or subtract. So in this case, I'm adding 6 all the time. And real life starts at 0, so we don't have a sequence, so it's just n. And n is down low, so I always remember that n is low when it's linear because I start at 60 and I have a constant increase and it's repeat adding. I'm adding 6 over and over and over again. And remember, repeat adding is multiplication, right? Like 6 plus 6 plus 6 is the same as 3 times 6. So repeat adding is multiplication. That's why the formula has multiplication. So our starting grade is 60 and then 6n. And what this does is it will predict future values. Now again, I don't know if we can get above 100% here, but let's say we can. So if I study 7 hours, what grade would I expect? So I'm going to sub in 7, and 60 plus 42 looks like it would be 102 either points or percent or something like that. And again, you know, this formula might only work for a short time. It might not work for always. And then if you're going to graph this, then it would be like what we've done in the past. Again, I, D, always. This is your input to your function. This is your output to your function. And so these go by 1. So, you know, the 0, 1, 2, 3, 4, 5, 6. And again, we just want to space these out consistently. And then these, let's see, they go by 6s, but that's kind of weird. You know, most people probably wouldn't go by 6s. So maybe I'll go by 10. So like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And again, sometimes we do that zigzag thing where we might skip some of these low grades here. So they're starting at 60. If I study an hour, it looks like it's just a little bit past 65. If it's 2, it's a little bit past 70, so 72. 3 would be almost 80, so 78. 4 would be at 84. And then again, I could keep graphing, but it's going to make a straight line here perfectly. It's going to keep going. And again, I would label these hours, and this would be like maybe percent grade or something. And then this is, I don't know, how studying impacts grades or something like that. But you can see it's definitely going to be linear, okay? And it's a constant increase. Now, if I want to talk about something that's exponential, we could talk about, oh, I don't know, say we have some termites. So not like we want lice or termites or anything like that, but say at day, and then we have the number of termites. And maybe this is in a forest where they have kind of an unlimited tree supply or wood supply to damage here, or even a house sometimes. So say that we start out with 2 termites, and then say they're growing. And so say this is 6 and 18 and 54 and 162. And it looks like they're getting big pretty fast. So I am guessing that this is exponential. And I can kind of see the pattern. It looks like if I times 3 times 3 times 3 times 3. Now remember, this is also a percent increase. So you could do percent change. It's not adding the same amount all the time. So if you're trying to figure out the percent of increase, if I take 6 minus 2, it went up by 4. And then remember, percent increase, you take the change divided by the beginning and then times by 100. So that's actually 100 or a 200% increase. So I kept the 2 termites and then I increased it by another 4 more. So if this is my 100%, you can see that's my 200%. So it's really a 300% increase total, okay? And so I can write my formula. So I have my starting amount, which is 2. And what math am I doing? Well, I'm multiplying by 3, and a lot of times we just use parentheses for that. And because it's exponential, my variable is up here. Okay, it's not down low like linear, it's exponential because, again, multiplying by 3 over and over again. Again, if you think of 3 times 3 times 3 times 3, that's exponential, 3 to the 4th. So this is definitely exponential. And I could just make my table go forever, but say I want to know how many termites we're going to have after 8 days. I'm going to write an exponent of 8. So 2 times 3 raised to the 8th power. And what is that? And so that's how many termites I would expect. And if I kept the table going, it should match. Now again, if you graph this, this is definitely not going to be linear. So if I make my little XY thing here, 0, 1 day, 2 days, 3 days, 4 days, 5 days, 6 days, 7. And remember, these are number lines, so you got to start at 0 and work your way up. You can't like start at 400. You got to go 0 and then that. These are getting big pretty fast here. So if I go by 2s, obviously I'm going to run out of space here. So I could go by 25s. I could go by maybe 20s. So I might go 20, 40, 60, 80, 100, 120, 140, 160, 180. And again, I'm not going to be able to, if I double that or triple that again, notice my chart would maybe have to go by 50s to get, something in the 500 range. So this is days, and this is number of termites. And let's see, and then I could say, termite population or something, or termite growth, or I can come up with any title that kind of fits what we're doing. So at 0, I'm way, down here at 2. At 1, I'm still down here at 6. At 3, or no, at 2, sorry, I'm at 18. But then at 3, it goes up to, 54. And then at 4, we're already at what, 162? So maybe about right there. So you can see this is going like that. So you can see how it's exponential growth. And again, it kind of starts out slow at first, and then it works a little bit different. All right, let's look at a couple other examples. Say that let's see, we could do, maybe we could do, I don't know, like crafts or something. So say I make up like crafts and maybe dollar amount or something. And so maybe this is the price that it costs to make some crafts. So we have 3, 5, 7, 9, 11, 13. And so you can kind of see that if you make 0 crafts, it still costs you $3. That's probably because of the supplies you bought. So you went to the store and you bought $3 worth of supplies that you need to maybe like scissors and a ruler, things that you're going to use over and over again. But then if you make 1 craft, it costs $5. So it could be that there's like $2 of supplies that craft makes, or maybe the kit, maybe the craft kit. So maybe we say that these are kits. So number of craft kits, and maybe you bought $3 of supplies that the kit doesn't give you, like again, scissors, a pair of scissors and a ruler. But then when you buy the kits, you get the supplies that you need to kind of make the craft. So if you change your mind and don't make any crafts, you're still out the scissors and the ruler. You lost $3. But if you make 1, it costs you 5, and so forth. All right. So if I look, it looks like it's going up by $2 all the time. And it's adding. So again, this would definitely be linear, okay, or the arithmetic like we did the other day. And so my starting amount is at 0, which is $3. So that's my scissors and my rulers or whatever. And then it's adding $2 all the time. And then again, linear, the n is down low, okay, because it's growing by repeat adding, which is multiplication. So again, I could predict if I want to make 8 crafts, how much it's going to cost me. So I'm going to put 8 in there. 3 plus 16 looks like 19. So let's see if that works. If I add 2, I get 15, add 2, 17, add 2, 19. So it does. So this formula predicts future values. And again, if I graph this, all right, so I would have 0 crafts, 1, 2, 3, 4, 5, and so forth. So this is what number of craft kits? And this would be what? Maybe the money I spend. And then this is like, I don't know, cost of making the crafts or something like that. Because the cost would include the scissors or whatever. Now again, odd numbers are kind of weird to put on a graph. Like we wouldn't normally put 3, 5, 7. So again, they're not getting big really fast. So I might just go like 1, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, and I could label these. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Just because my numbers aren't that big. I could go by twos, but I probably wouldn't go by odd numbers. I'd go by even. So at 0, it's $3. If I make 1, it's 5. If I make 2, it's 7. If I make 3, it's 9. Okay, kind of in the middle there. And again, this should make a straight line if I had a ruler and graph paper to graph that. All right, so another example might be something like, say that you inherit an antique clock. And say that I tell you that this clock cost $100 when was worth 100. So this is maybe the year and the money that it's worth. And maybe it's going up 10% per year. We call that appreciating. So when a car is worth less, it's depreciating, but this is appreciating. And so what we're going to do here is, right, you have your starting amount, $100. It's going up by 10%, so 110%, because you keep the clock value and you're adding to it. And again, when you're repeat multiplying or you have a percent, it's exponential. So you could put an X up there or an N, any variable. So what I could do is I could fill out my chart if I wanted to. So I could say 100 times 1.10, and I could raise that to the first power, and that would be $110. And then I could take that number times again. So I'm just going to take my previous answer times 1.10 again. Oopsie, I didn't like it. All right, so let's do 110 times, what was that, 1.10. So $121. Take that times 1.10. That's what, $133.10. Take that times 1.10. And I get $146.41. And I could keep going. But again, I could just go into the future somewhere. So say I want to figure out the value of this after 10 years. All right, so I could just take my formula and I could raise it to the 10th power and figure that out. So if I $100 times 1.10 raised to the 10th power, that would be what? 259.37. All right, and so that would be the value of it at that point. And again, if I graph this, it's not going to look super extreme. It's going to start out at 100 and it's going to kind of stay there for a while, right? And then eventually, it's going to slowly go up. So it's exponential. So, all right, hopefully that helps a little bit, just clarify a little bit what we did today, and we'll touch base tomorrow.